Observe the standard economy, a chaotic swirl of stock tickers, price signals, and abstract charts. But it hard resets into a stark architecture, a grid of basic geometric masses governed by physical force vectors. To understand the mechanics of this engine, we must discard concepts of value, of information, choice, and market signals. These are abstractions that do not exist in the material layer. This is the starting point for physicalist economics. In this framework, all economic activity consists of matter in physical spacetime undergoing concrete, force-driven events. Every event follows the rigid laws of motion and thermodynamics. If a specific force is applied to a specific mass at a specific coordinate, the resulting state change is a mathematical necessity. One material state forces the next, with no room for deviation. This makes the system hard determinist. Because every macroscopic event is the inevitable result of prior material conditions, only one sequence of events can ever unfold. There are no alternative histories. The initial states guarantee the macro outcomes. We analyze this system using only measurable physical variables: the displacement of objects, mechanical deformation under stress, thermodynamic phase changes, and the structural persistence of matter over time. When the behavioral illusions of standard theory are removed, the global economy resolves into a problem of engineering and thermodynamics. In a world of matter in motion, the human participant is biological matter. We define labor as biological matter generating and applying physical force to external structures. This diagram models the human arm as a biological heat engine. Biochemical fuel undergoes metabolic reactions, producing mechanical force vectors to manipulate tools. Decisions modulate this. Neural events are physical state changes inside tissue that determine the direction of outgoing force. This physicalist lens must also be applied to money. We must strip away its symbolic layer to see its causal role. Money consists of material configurations designed to elicit physical reactions. Here, the geometric pattern of a metallic coin triggers a sequence of neuromuscular state changes, causing a biological hand to grasp and move other matter. Electronic bank states function similarly. They are hardware configurations that cause automated machines and human hands to execute mechanical sequences. If a specific configuration of money fails to cause force-producing behavior, it remains physically inert. It performs no work. Human agency and financial capital are simply physical triggers within a deterministic chain of biological and mechanical states. Scaling up to the level of mining, fabrication, and logistics does not change these physical rules. These sectors form contiguous regions of one material field, linked by chained state changes. As this diagram shows, one material transition produces the physical conditions that mathematically necessitate the next. The deformation of one block provides the geometry required to move the next in the chain. Coordination is the temporal synchronization of these events, the alignment of machine cycles and biological rhythms proceeding without destructive interference. Markets function as routing architectures, physical layouts and marks constraining the direction of future sequences. Because these sequences occupy space and time, they are subject to the physicalist definition of a bottleneck. Here, a physical threshold maxes out. Bottlenecks are threshold effects: lack of spatial clearance, mechanical fatigue in a bearing, or metabolic limits of a biological body. When the applied load surpasses the material's tolerance, the sequence halts as physical law. Supply chain disruptions are inescapable limit breaches in the geometry of physical spacetime. In a hard determinist system, growth is a measurable physical change. Growth is an increase in the density and speed of completed material transformations per unit time. We see the spatial paths fill and the throughput accelerate. This acceleration is capped by the system's ability to dissipate heat. If the generation of thermal energy exceeds dissipation capacity, the system reaches a failure threshold. When these thresholds are breached, the system undergoes collapse. Collapse is the deterministic propagation of unfulfilled physical requirements through the network. The failure begins when a saturated heat sink allows a component to reach its thermal softening range. This softening causes a drift in dimensional tolerances, which leads directly to the seizure of a mechanical bearing. The seizure blocks a physical path, resulting in immobile queues of rigid bodies. The fracture propagates through the network graph until the entire system reaches gridlock. This propagation follows physical law. No alternative history exists after crossing the thermal threshold. Recovery occurs when the system settles into a lower activity level that no longer violates its structural thresholds. Economic crashes are mechanically identical to structural microcracks propagating through a piece of stressed metal. To see the ultimate conclusion of this model, we must view the planetary economy as a single entity. This planetary scale field tracks the real constraints of our world: thermodynamic flows, heat dissipation limits, and structural stress points. Transitions in one geographic region set the unalterable physical boundary conditions for all adjacent regions. This interconnected material field leads to a final, inescapable reality: the permanence of scarcity. In a finite material system, post-scarcity is a physical impossibility. Every state change requires non-zero spatial displacement and heat removal. On the left, a grain surplus decays because it occupies finite volume. On the right, a digital server farm is capped by charge stability and thermal density. Digital abundance is an illusion. It is strictly bound by device area, heat sinks, and the cross-sections of conductors. In a universe of permanent scarcity and absolute determinism, the role of planning changes. Effective planning is the pre-arrangement of physical constraint configurations. It is the strategic arrangement of spatial geometry and heat sinks to force future sequences along permitted paths before structural failure occurs. The economy is an engine. It cannot be manipulated through policy or belief. It can only be engineered by submitting to the absolute limits of matter, force, and thermodynamics.